Good morning. Today we'll be talking about sensors for flow. When we will work with flow, we will have two ways how we can define it and how we can measure it. It will be volume flow and mass flow. Some sensors will measure directly volume flow, some sensors will measure directly mass flow, and of course we can recalculate between the two kinds of flow if we know density. So first of all, volume flow is defined as some amount of liquid or fluid that will flow through some given area, but this amount is given as a volume. So for example, cube meters per unit of time. Mass flow, on the other hand, will be defined as an amount of mass flowing through some given cross-section per a unit of time. So the units here will be, for example, kilograms per second. And if we know density, then we can recalculate between the two kinds of flow. We can also use some other way how we can measure flow, except those two definitions of flow. It is typical for industrial sensors that they use some other principle, because basically the definition principle is not that robust, so it will not be good for industrial environments where you have vibrations, where you have changes of temperature and so on. So many flow meters will be based on measurement of flow or flow profile of the fluid, and then this is multiplied by the cross-section. So today we will see all those three possibilities. Some flow meters will measure volume flow or mass flow directly. Some other flow meters will use this principle that you measure speed of your fluid in a pipe and you know the cross-section. And of course you can use this to get volume flow or mass flow if you know density. The flow meters that will be based on direct measurement of volume flow or mass flow will be the ones used to calibrate all other devices. The flow meters based on measurement of speed, then they cannot be used to calibrate the other instruments. There are many principles used to measure flow. We will discuss only some of them. We will discuss only the ones that are highlighted in green here. So we can measure the flow if we measure differential pressure. This will relate to the pressure sensors that we have discussed in previous lectures. So this is basically done in such a way that you measure the pressure difference caused by some object that is preventing the flow, and there is a relation between the pressure loss and between the flow, as we will see in a few minutes. There are many objects that will prevent the flow. In those sensors here, we will use just orifice plates. You will see in a few minutes what that is. The others are nozzles, venturi tubes, pitot tubes, and so on. I have found a nice video that explains how all those devices work, so we'll not go in detail about those sensors. Then we will discuss an ultrasonic flow meter. This is a flow meter that is used to measure liquids in distribution lines, for example. We will then discuss an electromagnetic and Coriolis principle. So we'll discuss only 4 sensors today, but you see that there are many others like the vortex or thermal principle, which we will not cover in this lecture. So let's start with the differential pressure gauge, which is based on a measurement of differential pressure in front and behind some object. So let's imagine we have an orifice plate. An orifice plate looks like this. It's a sheet of metal with a hole in the middle. and you install that in a pipe like this. So the flow goes from the left to the right. Here you have some known cross-section and you have some known speed of the fluid. And by making this hole with a defined diameter that is smaller than the pipe diameter, you force the fluid to go faster, and you measure the faster speed will decrease the pressure. So if you measure the pressure in front and behind the orifice plate, you will see a difference in pressure. So if we look on the pressure during all this length, you will see that here, if the profile of the flow is steady, you will have a constant static pressure. Then in front of the orifice plate, you will have a small increase of the pressure because you're basically trying to block the fluid to flow. And then behind the orifice plate, you will have a sudden drop of pressure because, as it follows from the Bernoulli equation, if you are decreasing this diameter, you are forcing the liquid to go faster. And if you look on the pressure difference, from this pressure difference, you may calculate what is the flow rate of this fluid. Of course, we need to know something about the geometry, about the diameters. So if we compare the cross-section in front of the orifice plate and in the orifice plate itself, you may find out the equation. So here, this is an equation that is saying the conservation of mass. It means that you cannot lose anything in the sensor. So if you multiply this cross-section times velocity, you have some momentum, and the same momentum needs to be conserved also here. The A1 and A2 are the cross-sections of the pipe and of the orifice plate. And here you use also the Bernoulli equation, which gives you the relation between the speed, density, and pressure difference. And if you combine all this together, we'll find out that flow rate, that's what we want, is a function of pressure difference. You see here that's the pressure difference delta P that we measure. It is a function of density, so you need to know density of your fluid, which also means that you need to know temperature, because density is changing with temperature. And here, this is the geometry of the orifice plate, that's the cross-section D. And alpha and epsilon are coefficients that are based on the material and of the geometry of the orifice plate. So basically, this is all a constant value. If you have a constant temperature, then the density is constant as well. And you see that flow is dependent on delta pressure with a square root dependency. So it will not be a linear dependency. It will be a square root dependency. So it means that you either are satisfied with this or you need some way to linearize that. But there is definitely a relationship between the flow and the pressure that we measure. Now let's take a look on a video that will explain us in more detail how this works. The most important thing is where you place the probes for the pressure. So there are standards that say how far this needs to be placed. So they define what should be the diameter of those pressure probes and so on. And also there are standard orifice plates that give you the cross-section for some given cross-section of the piping. We'll discuss that in a few minutes. So let's take a look on the video, which is quite interesting and I think well made.
soon as the fluid starts to flow, its velocity around the orifice plate increases significantly because of the restriction in the cross-section. At the same time, due to the laws of fluid mechanics, the static pressure at this point decreases. Consequently, different values are detected in the pressure chambers of the sensor, a higher pressure before and a lower pressure after the orifice plate. This pressure difference is a direct measure for the flow velocity and thus the mass and volume flow in the pipe. The higher the flow velocity and the resulting drop in pressure around the orifice plate, the greater the differential pressure measured. In numerous industrial applications, the orifice plate covers many needs of flow measurement technology. However, other designs are available for certain measuring tasks to minimize undesired effects, such as excessive pressure loss or abrasion of components due to solids carried in the fluid. This demonstration shows that an abrupt restriction generates severe turbulence in a fluid. Nozzles with a rounded, funnel-like inlet clearly reduce turbulence and thus create less pressure loss. Nozzles are particularly suitable to higher flow velocities or to fluids with abrasive solid particles. Turbulence reduction is even greater with Venturi nozzles. And finally with Venturi tubes, where the restriction is created by longer conical constrictions in the pipe wall. All these designs can be supplied with different restriction diameter sizes, so that the pressure loss and the differential pressure generated can be optimized for the process conditions. Industrial flow measurement using differential pressure has been tried and tested in numerous applications worldwide for about 100 years. With this measuring principle, all liquids, gases, or steam can be measured, even at extremely high process pressures and temperatures. Every differential pressure flow meter manufactured by Andrus and Hauser is configured to customer specifications and pre-mounted.
Okay, so we've seen how it works. And now let's take a look on the properties of this orifice plate. So the construction is quite simple. It's a sheet of metal, and there is a hole in the center with some specific diameter. You also need to be very careful about the edges of this orifice plate. So the standard prescribes you how this should be chamfered. You can see that here there typically is another small hole at the bottom to allow sediments, if they are present in the fluid, to escape. Here you can see that we have the two pressure tabs here, downstream and upstream. The distance from the orifice plate and also their diameter is also defined by a standard. The orifice plate then typically is looking like this. So it's a really long device. Here you have the orifice plate. This is the difference pressure sensor as we already know it. And here you see there is a really long section of pipe in front of the sensor, and there is some defined section behind the sensor as well. I have here some example. So it can look like this. Here is the orifice plate. Those two are the pressure probes. And you see there is a really long section of the pipe in front of the orifice plate. So the flow rate needs to go like this. And why? Well, the reason is that if you want to measure with an orifice plate, you need a really long section here because you need a stable profile in the liquid. So a laminar flow needs to be created in front of this pipe, and if you have anything that prevents this type of flow, your orifice plate will not measure correctly. You need to do the same also behind the orifice plate. but it's not that critical. So behind the orifice plate you have a quite shorter section, at least 5 times pipe diameters, but in front of the orifice plate this this straight pipe needs to be really long. We'll see in the next slide a table that is saying how long that needs to be. If you look inside of the pipe, you will see that here there is a smaller diameter. That's the orifice plate itself. So here's the orifice plate. So the orifice plate is a simple device because it consists only of this sheet of metal, but it's a very sensitive. How do you install it in the application? So this length, it's the most critical condition that you need to fulfill. And if you do not fulfill that, if you install anything in front of it, then it will definitely not measure correctly. For small pipes, it's typically not a problem because for small pipes, you just need to maintain, let's say, 30 or 50 pipe diameters in front of it. But there can't be any walls, any bendings, any pumps, and so on. So this is the table I was talking about. This table is saying you how many pipe diameters you should keep in front of the orifice plate. And we'll see that it's a really long distance. It differs for different arrangements, so let's take a look first on this. Here you have the orifice plate. Here you have a full way open valve in front of it. Behind the orifice plate, it's not that critical. You just need to keep at least 5 pipe diameters. But in front of the orifice plate, you need to keep a long distance. And this distance also changes with the ratio of the pipe diameter to the orifice plate diameter, which is typically named as beta here. You see it's a ratio. So let's say I have the ratio, let's say 0.7, just a random value. And for the case of the straight pipe in front of the orifice plate, you see here I need to keep at least 20 pipe diameters in front of the orifice plate. So in this 20 pipe diameters, I cannot install any walls, any flaps. There can't be any bending at all. You just need to be a straight pipe so that you develop the flow profile in front of the orifice plate. And if you look in this table, this is the shortest distance for this straight pipe. If you have something in front of the orifice plate, such as a bending, for example, here we have an orifice plate, we have a bending 90 degrees, then we need to keep 29 pipe diameters. So again, it's a lot. For large pipe diameters, if you would have 50 centimeters, for example, pipe diameter, you would need to have 50 times, let's say 30, so 15 meters. So in many cases, it's not even possible to find a section in the piping that is straight and that does not have anything that prevents the flow. For example, this case, you have a 90-degree bending in 2 directions, so like this and down. And here you see it's this line C, and you have 63 pipe diameters. So for 1 centimeter pipe diameter, you need to keep 63 centimeters in front of the orifice plate. Behind the orifice plate, it's always 5 pipe diameters. So based on your configuration, you need to find a section that is straight and that does not have anything that prevents the flow. So this is the biggest disadvantage of the orifice plate. It's simple, it's reliable, it works in a really large range of temperatures, but the installation is a problem. The orifice plate is installed in the pipe, and then we connect this to a differential pressure gauge. We have discussed that recently, so it looks like this. And you have one pressure probe here, one pressure probe over there, and you measure the pressure difference. You see there are valves installed here at the pressure probes. If you want to remove the pressure sensor, clean the system, replace that, calibrate that, and so on, you don't need to interrupt the process. You just close those valves and that's it. Since the flow rate depends also on density, you typically have a temperature sensor installed nearby so that you measure the temperature and calculate density. You can see that this pressure difference and temperature then goes to something that's called a flow computer, which basically calculates the equation that you have just seen and gives you just a flow rate in the selected units. So sometimes it's an external unit, sometimes it's directly embedded into the sensor itself. So what are the advantages of orifice plates? It works for all fluids, whether it's a liquid, gas, or steam. It works for high pressures and high temperatures, so up to 1000 centigrades are easily doable. You can see pressure. Those numbers are selected from data sheets from industrial flow sensors with orifice plates. So 42 megapascals, so high pressures and high temperatures. You can separate the pressure sensor with the separation liquid, as we have seen that last week. So it's not a problem to have high temperatures as well. If you have the valves installed, you can exchange the orifice plate or the pressure sensor without interrupting the process. So if you just need to exchange the differential pressure gauge itself, you just close the valves, replace that, and close it again. Of course, if you need to replace the orifice plate, you just need to interrupt the process, close it, remove the orifice plate, and replace it. It is usable for wide pipe diameters. The standard orifice plates are for diameters larger than 50 millimeters. So if it's larger than 50 millimeters, you can use a standard orifice plate. If your pipe has a small diameter, you can use a similar orifice plate, but it's not defined in the standard. And you can use it for those diameters, so it works from diameter 10 millimeters up to more than 5 meters. The standards are not from 10 but from 50 millimeters, but it works also from 10 millimeters. For larger diameters, we are not using orifice plates, but we are using pitot tubes, which work in a little bit different way. But it's basically also the same principle that you measure the pressure and relate this to the flow rate. So those are the advantages of orifice plates. What are the disadvantages? It has a limited turn-down ratio. Turn-down ratio means the ratio between maximal and minimal flow that you can measure. So it cannot measure from zero flow. This would mean that you measure zero pressure difference. So there is a minimal pressure that you can measure, and therefore minimal flow. And there is also a maximum flow that you can measure. And for the orifice plate, typically the turn-down ratio is somewhere between 5 to 1. So let's say if you measure flow rate of, let's say, 5 cube meters per hour or per minute, if this would be your maximum flow rate, then the minimum flow rate you can measure with that would be 1 cube meter per minute, for example. So this has a quite limited ratio between minimal and maximal flow rates. The orifice plate is not a good device if your fluid can damage the orifice plate. So it means if it has some particles, some impurities in the fluid, you cannot use an orifice plate. Or an orifice plate can be eroded over time by the particles in the fluid, and therefore you can use it only for clean liquids, vapors, and fluids. So it's only for clean mediums. And the biggest disadvantage of the Orifice plate is the installation. You have seen that it requires a really large distance in front of the Orifice plate, otherwise it will not work correctly. So if you are limited in space, then the Orifice plate is definitely not a good sensor to choose. Other disadvantages, it's not working for small flow rates. It's clear because if I have a really small flow rate, then I will have a really small pressure difference. So typically it does not work for flows smaller than 2 liters per hour. It does not measure liquids that are really viscous, so if it's like a honey or even thicker, then it's not working. If you look on other principles, especially the Coriolis flow meter that we will discuss at the end today, this Orifice plate cannot measure directly density, concentration, or viscosity, which can be done with the Coriolis flow meter. So it measures you only the flow rate, and you need to add the temperature if you want that to be correct. And as I already said, it's not working for abrasive liquids, so mining applications where you have mixtures of water and sand, for example. Orifice plate is definitely not a good sensor for this application. Okay, a second flow sensor will be an ultrasonic flow meter. We will install the ultrasonic flow meter in a pipe, and we will have 2 piezoelectric transducers that will transmit ultrasonic pulses through our fluid. So here we have the fluid that is flowing in the pipe. Here we have a pair at the same time, and here we have a second pair of piezoelectric transducers, so a receiver and a transmitter. We transmit an ultrasonic pulse from this transmitter. It goes through the fluid, gets reflected at the other end of the pipe, and the reflection is received by this receiver. And we measure how long did it take before I got the reflection. And then I use this as a transmitter. I transmit a pulse against the stream, and I receive it here with this receiver. So when the flow is 0, the time it takes from this transmitter to this receiver will be the same as it will take from this transmitter to this receiver. If there is a flow from left to the right, then from this transmitter to this receiver it will take a shorter time, and here against the flow it will take a longer time. So based on the difference between this time and between this time, we can find out what is the speed of the liquid, and we multiply that by cross-section, and we will get the flow rate. So here we already see what will be one disadvantage. The pipe needs to be completely full, because if it's not full, we multiply that by some cross-section, but we multiply it by the cross-section of the pipe, and it's not filled, so we cannot see the correct profile and correct flow rate. Let's take a look on the video again that explains this. Again, from the same company, they are manufacturing mostly flow meters. The introduction is always the same.
Vegetable oils in the food sector, fluids in primary industry, or petrochemical products. The fluids flowing through pipes Inside the ultrasonic flow meter, pairs of sensors are fitted across from each other in the measuring tube. Each sensor can alternately transmit and receive an ultrasonic signal. Simultaneously, the transit times of these signals are measured. The ultrasonic signals are generated with piezoelectric crystals applying a voltage. Conversely, a piezoelectric crystal creates a voltage when an ultrasonic signal impacts the sensor. By increasing the number of sensor pairs, it's possible to accurately detect and mathematically compensate for flow profile distortions over the entire pipe cross-section. When there is no flow, the signal transit times are the same, upstream and downstream. Once the fluid starts to flow in the measuring tube, the ultrasonic signals are accelerated in the direction of the flow and decelerated against the flow. As a result, the ultrasonic signals now have different transit times, less time in the direction of flow and more time against the flow. Therefore, the differential transit time measured by the sensors is directly proportional to the flow velocity in the pipe. Together with the known tube cross-section, the actual flow volume can then be calculated. The greater the flow velocity, the greater the measured time difference between the two ultrasonic signals. For ultrasonic flow measurement, the sensors do not necessarily have to be fitted into the pipe wall. With a clamp-on system, for example, the sensors are fastened directly onto the outside of the pipe. They can be retrofitted at any time without interrupting the process. With clamp-on sensors, the ultrasonic signal is passed directly through the pipe wall and into the fluid. The signal continues through the fluid, is reflected on the opposite pipe wall, and then measured by the second sensor. In this example, with a two-traverse installation, the clamp-on design is unique because flow rates can be measured in very large pipes, up to 4 meters in diameter. This possibility increases the areas of application, for example in the water and hydroelectric industries. Flexible mounting, process safety, and cost-effectiveness are the distinctive advantages of ultrasonic flow measurement. For all
Okay, so let's take a look what's inside of a flow meter. So we have seen that there is a piezoelectric crystal that generates the ultrasonic signal. So this is it. This is the piezoelectric crystal. When you apply voltage to this crystal, it creates oscillations, and those oscillations are then transferred through the fluid to the opposite wall of the pipe, where they are reflected, and this is received by the receiver, which is also a piezoelectric crystal, so that it creates you a voltage again. So based on the difference in time, we can get the speed of the fluid, and times cross-section, we can get the flow rate. What are the limitations? The limitations are that it will not work when you have a mixture of a liquid and gas. So if you have bubbles in the liquid, typically you need to keep the gas content under 2%, because if you have bubbles, it will prevent the ultrasound signal to be transmitted through the fluid, and it will be blocked and you will not receive the signal at all. The same happens also with solids, so you need to limit the amount of solids under 5% by volume. For the same reasons, the particles, they will block the transmission of ultrasound. You should not place the sensor on top of the pipe, simply because of the bubbles. So this is what happens here. You have bubbles on top, and this prevents the ultrasound from transmission. The same happens also if you install the sensor on the bottom. So if you have eventual sediments on the bottom, they will prevent the ultrasound from transmitting. So you should install the sensor from the sides of the pipe. And also it's not working for pipes that are not full, simply because we measure the speed times cross section. So you need to install that in a position that makes sure that the pipe is full at all times. This is the reason why here we need to prevent the bubbles or particles. So if you have bubbles or particles in the liquid, then you can have multiple echoes. The signal will be attenuated and it will be difficult to receive the signal. So it's not working for this kind of liquids. And we have seen on the video that you don't need to install the sensors directly in the pipe so that it can be clamped on from the outside of the pipe. So then it typically looks like this. So here you see transmitter plus receiver clamped on from the outside on the pipe. This also means that you can measure with the ultrasonic flow meter also aggressive liquids, because the sensor itself is not in direct contact with the liquid. It just goes through the wall, so you can quite easily protect the sensor. It works for relatively high temperatures, it works for relatively high pressures, but definitely lower than the orifice plate. What can you expect? It can measure liquids and gases, so no steam, and the liquids and gases needs to be clean, so no bubbles, no sediments. The typical accuracy when you install the sensor in a process is about 2%, so it's not bad, but it could be better. If you install that in a lab under reference conditions, then you can expect that you have an error for, let's say, roughly 0.5%. It can measure small and large pipe diameters. The clamp-on system up to 5 meters. The inline system up to 2 meters. So the inline system means that you have the sensors installed in the pipe wall within an armature, and the clamp-on is that you have these sensors from the outside. It can measure roughly in this temperature range, so from about -50 to +170 centigrade, so definitely smaller maximum temperatures than the orifice plate, but it's still a large temperature range. Other advantages are that it has a large turn-down ratio, so it can measure both large and small flow rates. The ultrasonic sensor has the turn-down ratio roughly 50 to 1. The orifice plate had roughly 5 to 1. So we can have about 10 times larger range compared to the orifice plate. If you use the clamp-on design, it will not create any pressure loss at all. It's simple straight pipe, so no pressure loss at all. The orifice plate creates a permanent pressure loss. There is no abrasion or corrosion from the fluid, so you can use it for aggressive liquids. You can use it if you have a small amount of abrasive particles in the liquid. It measures in both directions. The orifice plate measures only in one direction, so that's also an advantage. And if you install the clamp-on system from the outside, you can measure or change the sensor without any process interruption. For the clamp-on system, the price of the sensor is virtually independent of the price of the pipe diameter. If you have smaller pipes, larger pipes, then it's still the same sensor. It differs only in the adapter that you use for installation. Of course, it has some disadvantages. It cannot measure small flow rates, such as flow rates below 2 liters per hour. It is not suitable for viscous liquids, so if you have something like honey or something even thicker, then it will not work. It does not measure steam. Orifice plate was able to measure steam. It is not good for measuring liquids with suspended solids or slurries. It does not measure mixtures of gas and liquid. And if you have the clamp-on system, there is no traceable calibration to a standard, because every time you install it, the installation is a little bit different, and hence you cannot trace it back for some calibration. How about the examples? So the industry that are using this ultrasonic flow meter are chemical industry, petrochemical industry, water supply. You may find videos where they have examples of those ultrasonic flow meters clamped on really large pipes for hydroelectric, for plants, for water supply, for cities, and so on and so on. This is an example of the clamp-on system. So here you see it's a vertical pipe. Here the transmitter and receiver, the signal travels like this, and you just clamp it on the pipe, and you don't need to interrupt the process, and you see what is the flow rate. So this is the inline version where you need to install it in the pipe. This is the clamp-on system. For the clamp-on system, you see it works for large pipe diameters, so here they say up to 4 meters. You can find out even larger, like 5 meters diameters. The clamp-on system, typically a smaller diameter, so for this particular sensor, you can find out 200 millimeters. The calibration is made for 1.5% of range. But you can find different devices for larger pipe diameters, typically up to 2 meters. The installation is less sensitive than an orifice plate, so it means that you still need to keep a distance in front of the sensor and behind the sensor, but this distance is smaller in front of the sensor. Behind the sensor, it still remains roughly 5 times pipe diameter. In front of the sensor, for example, in a bending, here you had we have 5 pipe diameters. For the orifice plate, we had at least 20 pipe diameters. So it will fit into smaller spaces. The same for pumps, for example, at least 15 pipe diameters. Valves need typically at least 10 pipe diameters. If the valve can be controlled, it means it's not fully on or fully off. So you can change the flow rate with the valve. If you just have a fully open valve or fully closed valve, then you can keep at least 5 pipe diameters. So the installation is more convenient. It fits into smaller systems. You still need to install it correctly. So you need to make sure that the pipe is full at all times. So typically you need to install the flow meter in a vertical direction. We'll see the same problem also for the 2 other sensors. So all that will apply for the 2 remaining sensors will also apply for this ultrasonic sensor in terms of installation direction. Any questions so far? Okay, good. The third flow meter will be the electromagnetic flow meter. The electromagnetic flow meter is good only for liquids, and the liquid needs to be conductive. The principle is quite easy. You have a magnetic field that is created by a coil or by a permanent magnet. And when you have a conductive liquid that is moving inside this magnetic field, you will get induced voltage. That's basically Faraday's law. So in the perpendicular direction, you install two electrodes and you measure the voltage that you have on those electrodes. The voltage is very small. You see, it's roughly 300 microvolts per 1 meter per second of velocity. It, of course, depends on the material, so on the properties of on the conductivity of the liquid, and it depends also on the speed. That's what we want. So what you measure at the end is a voltage on the electrode, and this voltage will be proportional to the speed of the liquid that you have inside the pipe. So then you have a speed times cross-section will again give you the flow rate. We typically create the magnetic field with a coil because we need to reverse the polarity of the magnetic field. You will see the reason on the video. And so the signal that you have on the coil typically looks like this. So you apply some positive voltage on the coils. This creates you a magnetic field, and you sample what is the voltage. Then you reverse the polarity. You apply a negative voltage with the same amplitude, and you measure it again. So this allows you to compensate for external magnetic fields, for example. Let's take a look on the video. It again explains how this works.
The most diverse substances are transported and distributed in piping systems every single day. They may include drinking water, fruit juices, chemicals, or even slurries containing stones. The fluids flowing through pipes often have completely different properties. Consequently, there are different principles for their measurement. One method is flow measurement based on the electromagnetic principle. The basic physics of this principle can be traced back to the English physicist Michael Faraday, who in 1831 discovered that electrical current can be generated with a magnetic field. Roughly 100 years later, the Swiss inventor and priest Father Bonaventura Turliman applied this knowledge to electrically conductive liquids flowing in pipes and built the world's first electromagnetic flow meter. Let's take a closer look at how this measurement method works. Two field coils are located inside each electromagnetic flow meter. With the help of what are termed pole shoes, these coils generate a constant magnetic field over the entire cross-section of the measuring tube. Two electrodes, which can pick up electrical voltages, are installed at a right angle in the wall of the tube. The lining fitted on the inside wall prevents electrical short circuits between the conductive liquid and the metallic tube. If there is no liquid flow, no induced electrical voltage is measured at first between the two electrodes. The electrically charged particles of the conductive liquid are evenly distributed, shown here in water with red and blue particles. However, as soon as the liquid starts to flow in the measuring tube, the magnetic field applies a force to the charged particles. As a result, the positively and negatively charged particles in the liquid are separated and collect on the opposite sides of the tube wall. Now an electrical voltage forms, which is detected and measured by the two electrodes. This voltage is directly proportional to the flow velocity in the pipeline. Together with the known successfully used for this purpose is to create the magnetic field with a pulsed direct current. To do so, the polarity of the magnetic field is alternately reversed, illustrated here in slow motion. The voltage picked up on the measuring electrodes now constantly changes in polarity. As a result, all constant interference voltages can be eliminated. For example, electrochemical effects in the liquid, or external electromagnetic fields. Thus, the size of such interference voltages has no impact whatsoever on the actual measuring signal. The advantages of this are a stable measurement and a stable system zero point. With an installed base of over 1 million electromagnetic flowmeters, Endres and Hauser has stood for flow expertise and superb product quality for over 30 years. In other words, high accuracy, easy installation, and absolute reliability. For all applications, we have the right solution.
Okay, so let's take a look on what's inside. So we've seen that there are two field coils. So this is a field coil and this is a field coil. It creates the magnetic field with the help of a pole shoe, which looks like this. So this is a ferromagnetic material. It distributes evenly the magnetic field through the pipe in this direction. And then here in the perpendicular direction you have the two electrodes that pick up the voltage. So this is the measurement probe, and there is another one from the other side of the pipe. You need to install this in a non-conductive material to prevent short circuits. So here you have an example of a polyamide lining, but it could be also a different material for different application. Here are some examples of those electromagnetic flow meters. So areas such as food industry, chemical and processing industries. You see water supply. Water is conductive also, so it can be used for water. You can see here the materials, PTFE, that's Teflon, so from -40 to 130 centigrades. Different materials such as rubber here, 0 to +80 centigrade. So different materials are good for different temperature ranges. You can see the diameters here, so 150 millimeters, 100 millimeters, 2.4 meters. So the diameters are a little bit smaller than for the ultrasonic flow meter, but they are still quite large. What can you expect? It's based on conductivity. If your liquid is not conductive, then it's not working at all. So this flow meter can be used only for conductive liquids. Water, if it's, let's say, standard water and not deionized water, it's conductive, so it can be used also for water. The typical accuracy is about 0.5%, so it's quite an accurate device. And it can be used typically for pipe diameters up to 2.5 meters. The pressures are smaller than the Orifice plate, so here you can see 4 megapascals, and the temperatures are smaller as well. Let's say the same range like the ultrasonic flow meter, up to 180 centigrades. For the Orifice plate we had roughly 1000. It has a very large turn-down ratio, so the ratio between minimal and maximal flow it can measure. So this electromagnetic flow meter has a turn-down ratio of about 1000 to 1. The ultrasonic had 50 to 1, and the Orifice plate had 5 to 1. So this can measure in a really large range of flows. It does not have any pressure loss, the same like we had for the ultrasonic sensor. There are no objects that prevent the flow, so no pressure loss. It can measure liquids that are highly abrasive, like mixtures of water and sand, for example. So we could not measure this with the Orifice plate, we could not measure this with the ultrasound, but we can measure those mixtures with the electromagnetic flow meter. What are the disadvantages? Well, the major disadvantage is that it's not working at all for non-conductive liquids. It can have problems with sediments since we are still measuring the speed of the liquid times cross-section. So if we have sediments, we have a smaller cross-section and we do not calculate the flow correctly. It's not working with cryogenic fluids like liquid oxygen, argon, and nitrogen. It cannot measure steams or gases, and it works only if your pipe is completely full. So the same like for ultrasonic, simply because you multiply speed times cross-section, and if the cross-section is not full, you don't multiply that with the correct value. So how to install? Here you have the measurement electrodes that are in the horizontal direction. The field coils are in the vertical direction, and what's the most important is that the pipe must remain full at all times. Otherwise you do not measure the correct cross-section. So you should never install the flow meter like this in a horizontal pipe when the flow is going up. Here you do not know if the pipe will be full at all times, and you should never install the flow meter in a vertical pipe where the flow rate is going down, simply because here you may have bubbles. Here the water may flow, the liquid may flow, but you cannot be sure that the pipe is full at all times. So the correct installation can look like this. For example, if you have a horizontal pipe, then you install the sensor in this way. This makes sure that the flow meter is always below the eventual liquid level in the pipe, and that this system is full at all times, and then you have the known cross-section and you know it's full. Here note also that you have the valve here, and this allows you to remove sediments from time to time, and the sediments will accumulate at the lowest spot in the pipe, and the bubbles will accumulate here or here at the highest spot of the pipe. So this makes sure that you install it correctly. It is also sensitive to the correct distance behind the flow meter and in front of the flow meter, but here it's even less sensitive than the ultrasonic flow meter. So after the flow meter you need to keep at least 2 pipe diameters, so very small distance, and in front of the flow meter at least 5 pipe diameters, so it's roughly the same like for the ultrasonic flow meter. So here you see an example of the installation. So a horizontal pipe going like this was interrupted, then it's going down. This is the valve to remove the sediments. This is the flow meter, 5 pipe diameters, 2 pipe diameters here, and the flow meter is installed below the axis of the horizontal pipe so that we are sure that it's full at all times. So the ideal mounting of this kind of flow meter is in a vertical pipe. This is the same also for the ultrasonic flow meter. This mounting, when the flow rate is going up like this, makes sure that this is full at all times, that the sediments accumulate at the bottom and the bubbles accumulate at the top. So this is the best installation position for ultrasonic flow meter, for electromagnetic flow meter, and also for the Coriolis that we will discuss at the end today. It ensures you that you have enough pressure so that this is full at all times, avoids cavitation, which means that when you decrease the the pressure, you may create bubbles, and it makes sure that the meter remains full at all times. Okay, and the last flow meter for today will be the Coriolis flow meter. All those previous 3 cases of flow meters were based on measurement of speed times cross-section. The Coriolis flow meter, on the other hand, is different. It measures directly mass flow. So it will give you directly mass flow, and you don't need to calculate anything. The Coriolis flow meter is based on the effects of the Coriolis force. I have found a nice video showing what is the Coriolis force. Imagine that you have a pipe like this, and there is some flow of liquid in this pipe. You can make the pipe vibrate, so it will move up and down, and here we will see the effects of the Coriolis force. Maybe I'll just run the video first. You can try it at home in summer with a normal garden hose. So here you see this is a loop which you will find in the Coriolis flow sensor, and when there is no flow rate, you make it vibrate like this. It will move uniformly. When you apply flow rate, the Coriolis force will have a different direction at this side and at this side, and we will be able to measure it. So let's take a look. So this is without flow. So you see a uniform motion forward and backward. And when you apply flow, then we will see the Coriolis force. You see this wobbling. It means that there is a flow rate. Now this is what happens with the flow. So the Coriolis force has different directions on this side of the pipe and on this side of the pipe. So this is basically what's inside a Coriolis flow meter. Of course, the motion is not significant as here on the video. Basically what is happening is that you have the liquid that is moving, and it tries to move in this direction. When you apply this movement to the liquid here at this area, it creates the force that is acting in this direction. So it tries to continue moving straight, and when it moves here, you are forcing it to go back, and here at this area it tries to move in the opposite direction. So as we have seen on the video, when you don't have any flow, this is what happens. You have a uniform motion that you apply on the pipe. You can do it with one pipe or even with 2 pipes here. So without flow, you have a uniform motion forward and backward. With flow, you see this movement. That's the effect of the Coriolis force. And then basically you measure the frequency of this movement, and you also measure the distance between this pipe here and this pipe here. And there will be a relation between the flow and between the movement. We'll see that in the equations in a few minutes. So let's take a look again on a video. Right.
The most diverse substances are transported and distributed in pipelines every single day. This may include drinking water, fruit juices, oil and gas, as well as chemicals, acids, or alkalis. such method is flow measurement based on the Coriolis principle. The French physicist Gaspard Gustave de Coriolis set out the physical basis for this measuring principle over 200 years ago. What is interesting is that the Coriolis principle allows the flow of mass to be directly measured. Let's take a closer look at how this measurement method works. A tube is located inside each Coriolis flow meter. An exciter causes this tube to oscillate constantly, here in an exaggerated example. If there is no flow, the measuring tube oscillates uniformly. Sensors are located at the inlet and outlet and register this basic oscillation precisely. As soon as the fluid starts to flow in the measuring tube, however, additional twisting is imposed on the oscillation as a result of the liquid's inertia. Now, due to the Coriolis effect, the inlet and outlet sections of the tube oscillate in different directions at the same time. The highly sensitive sensors pick up this change in the tube oscillation in terms of time and space. This is known as the phase shift and is a direct measure of how much liquid or gas is currently flowing through the pipe. The higher the flow velocity, and thus the total flow, the greater the deflection of the oscillating measuring tube. The application of the Coriolis measuring principle doesn't stop here. It can also be used to simultaneously determine the density of the flowing fluid. To do so, the sensors also register the oscillating frequency. In other words, how often the measuring tube moves back and forth in 1 second. From the animation, it's clear that a tube filled with water oscillates more frequently than a tube filled with honey, for example, which has a far higher density. Thus, the oscillating frequency is a direct measure of the fluid's density. Both the density and the flow are determined simultaneously, but independently, via the tube oscillation. Endress and Hauser has continuously revolutionized and perfected Coriolis flow measuring technology in numerous innovative systems. This measuring technology is unique, as it's the only way multiple process variables such as mass flow, volume flow, density, temperature, and even viscosity can be measured simultaneously in pipelines. For all applications, we have the right solution.
Okay, so now again let's take a look what's inside. So inside we need to have the tube that we make oscillate. So if you take a Coriolis flow meter apart, it looks like this. So here this is the tube, this is the driving system which applies the oscillations, and those are the two position sensors. We have discussed the position sensors as well. Typically those are inductive sensors. And then you look for the phase shift here between the signal and between the signal, and this gets converted into the flow rate. As we have seen, the Coriolis flow meter gives you directly mass flow, and it can give you also density of the liquid. Here you have an example of the flow meter with two tubes. So if you have one tube, you measure the moving and the twisting. If you have two tubes, you measure the relative motion between those two tubes, which compensates also external influences like vibrations, external motion. So it allows you to compensate for all this. The tubes are made from stainless steel, typically for temperatures higher than 100 centigrades. They can be made also from titanium, for example, if you require that for the process. The bending of the tubes creates this Coriolis force, but you can also measure the bending, the movement also for straight tubes, which is typically made from titanium for higher temperatures. So it works both with straight tubes, also with the bended tubes. As we have seen on the video, we can measure the mass flow and we can measure the density. The density is measured by looking at the oscillation frequency of the tube. So for example, if you have two tube system, one tube and second tube, you apply the motion and the resonance frequency of the system will be dependent on the density of the liquid that is inside by this equation. So here this is the density times the volume in the tubes which you know, and the resonance frequency depends on the density of the tubes. So you can get the flow rate and the density independently. Yes?
I'm just wondering how much it depends on the driving force or what the driving system is.
It does depend, yeah. But since you know it, if you apply that, it's doable. Okay, so what are the advantages if you compare the dual and single tube system? So if you have a single tube system, it is sensitive to external disturbances like vibrations, for example. The dual system is internally balanced, so you suppress those external disturbances. On the other hand, it typically has a higher pressure loss. The single system has a smaller pressure loss. You use a larger pipe diameter, so that gives you a larger pressure loss here and lower pressure loss here. The advantages of the Coriolis flow meters are that it measures directly mass flow and density. It can measure temperature as well. The typical sensor used in this Coriolis flow meter is a PT1000. It is a very accurate sensor. The typical accuracy is 0.1% of range. So out of those 4 that we have discussed so far, it is the most accurate one. It does not require any distance in front of the sensor and behind the sensor, so you can install it anywhere you want. It can also calculate volume flow because it measures directly mass flow but density at the same time, so it can calculate volume flow. It can calculate concentration typically of a single phase liquid, so it's like a mixture of sugar and water and alcohol, for example. It can also calculate viscosity. Other advantages are that it can be used to measure small flow rates, so under roughly 2 liters per hour. The 3 previous sensors were not able to do that. It is fine for cryogenic liquids, so very small temperatures. It can be used for smaller pipe diameters than the other principles, so roughly 500 millimeters is the maximum size of the sensor. It can work for large pressures. Those numbers are again from some data sheets for the flow meters, so they say 51 megapascal and about double the temperature range compared to ultrasonic or electromagnetic flow meters, so up to 350 centigrades. What are the disadvantages? Compared to the ultrasonic flow meter and electromagnetic flow meter, it has a higher pressure loss. It performs the best with single-phase liquids if you want to measure concentration and viscosity, because if you have more components in the liquid, it has an impact on accuracy. And the biggest disadvantage is high price. It's much more expensive than the ultrasonic or electromagnetic flow meters. How does it look like? Typically looks like this. So it has this typical shape. Under this cover there is the pipe, the bended pipe, and you can directly tell, okay, this definitely is a Coriolis flow meter. So then if you have some distribution system like this, you see, okay, there are many flow meters installed. The flow meter is also sensitive on the installation, and you should never install a Coriolis flow meter in a horizontal pipe like this with the bendy tube facing down. The reason is sediments, because if you have sediments in the pipe, it will change the properties of the system, and plus there is no way how you can remove it unless you apply high flow rate to flush it out. If you install it in this way with the bending facing up, it's also wrong, because then you may have the same problem with the bubbles. So do not install the Coriolis flow meter in a horizontal pipe. It should always be installed in a vertical pipe, and it should be installed in such a way that the flow rate is going up. So this ensures you that the sediments remain here, the bubbles remain here, the system is full at all times, and it's the same rule like for the ultrasonic or electromagnetic flow meter. So do not install it like this because of the bubbles. Do not install it like this because of the pipe is not full. So this is the correct way how you should install it. If I go back to this picture, then we can say, okay, the flow definitely goes up here and up here to some distribution system. So never going down, never in a horizontal pipe. Questions? No questions, okay, good.